Okay, so our goal today, the atomic spectrum, is to figure out how color tells us about atoms. Oops, sorry. How does color tell us about atoms? So I started off this unit with the flames on the desk. Every element gave off a specific color. And we want to talk about how those colors tell us about those atoms. Okay. So in order to do that, we need to know a little bit more about light and how we can work with it. One of the first devices they used when working with light was called a prism. Okay. And a prism is just a triangular shaped piece of glass. Like this. This is a prism. Just a triangular shaped piece of glass. Okay. And passing it through a prism separates that white light into its component colors. So if you take white light, the thing we see as white light is really a combination of all the colors. And passing it through a prism, we can separate into, it's going to look like a rainbow. White light, we'll see, goes, I put them as distinct lines, but really it's gradually from red all the way to purple. Okay? So white light's got all the frequencies of light in it. Okay? So, and there's another device that does the same thing called a diffraction grating. So I'm going to show you those two things and what I mean by it separates into all the colors. So, it's dark in here. I worked hard on that. Okay, so I've got this projector so it puts just one light. And actually, you're going to want to look that way. And I'm going to put the prism in front of that line of light. If you look off to the sides, I got to get it right in the middle of the light. There we go. Up on that side, you can see a rainbow on each side, right? See the rainbows on the walls? Okay, that's because the white light is being separated. Notice both rainbows have red closest and purple furthest from the middle. That the rainbows are mirror images of each other. Everybody see that? Okay, so prism separates it into rainbows. The rainbows are always separated as mirror images. Okay, a diffraction grating does the same thing. Okay, so that's a diffraction grating. All that is a piece of plastic with, I think it's 12,000 lines per centimeter scratched into it. Okay, all it is, and so it's just like the back of a CD. I could have gotten that same rainbow by bouncing the light off a CD. Actually, but the important part I want to talk about is, notice that they're mirror images again. That purple is closest, red is furthest, and there's not just one rainbow. There's one over here too. There's one there too. That it's a rainbow, then another rainbow. Okay? A rainbow, then another rainbow. There's actually another one, we just can't see it because it's too bright in here. Okay? Doesn't feel real bright in here, but it is real bright. Okay, everybody okay with this? Okay, so what if the light is not white? Okay. Well, there's several ways of making the light not white. First, I want to show you the boring way, just to show you how color really works. Okay, so got my rainbow projected up on the screen, right? Everybody see the rainbows? Okay, so actually I need to move that one off the... Okay, so what I'm going to do now is I've got some blue food coloring in water, and I'm going to put that in the middle of my rainbow. And look what it does to the rainbow. It subtracts the red and the yellow. No, it subtracts the red almost to the yellow. So the red and the orange are subtracted. See how the middle where that blue is, on the sides of that, you do not see any red or yellow. Okay? These are dyes. Dyes work by subtracting colors. So this absorbs from red to yellow. Notice that blue is pretty much in the middle of that. That's why we see it as blue. Okay? If I put red food coloring in front of it, the blue and the, right? So it takes away the other side of the rainbow. And red's right in the middle of that. If I put yellow in front of it, yellow subtracts the blue and the purple. It's hard to see because it's, you can't really see. So see the blue and the purple below? Okay? And it's not there up above. So yellow just subtracts away the blue and the purple. But that explains things like, all right, so I got yellow. Yellow's on, I'm going to put yellow up top and blue on the bottom. Okay? So the yellow subtracts the blue and the purple. The blue subtracts the orange and the yellow. And if I just take the yellow and put it on top of the purple, just stack the beakers, I get green. Because the yellow takes off one side, the blue takes off the other side, and all you're left with is the green that's in the middle. And that's why yellow and blue make green. Okay? Yellow and red make orange because they subtract both off the blue side. Okay? Right. So that's dyes subtracting colors. Those are absorbed colors. Okay? But when I had the flame, I was emitting colors. Right? Okay, so we got to see what happens when you emit colors. So to do that, you're going to need diffraction gratings. Luckily for me, I happen to have some. So these glasses all have diffraction gratings in them. So when you look at them, no, they're not 3D glasses, they're diffraction gratings. So just like the one I projected through there, you're going to be able to see. Now again, don't try to touch these. Leave the plastic alone. So just handle them by the earpieces, so we don't fill up those scratches with human sweat. Okay. Okay. So first thing I want you to do is to look up at the lights in the ceiling. Okay, so look at the lights in the ceiling. You see that you got a copy of a rainbow for every one of those lights, right? It's actually too bright in here, it's hard to see. So try it now, it might be a little bit more clear. Okay, so you see rainbows everywhere. Now, this is my convincing you that this is diffraction gratings. Everybody convinced? Okay, so he said if the white light is not white, this is neon, okay, neon gas, and it'll pass electricity through it. Well, got to make it darker in here. It's always the challenge. Okay, so this is what we're trying to explain. Okay, If you're looking at right, we only want to look horizontally. Ignore the ones that go up and down. But you'll notice that it's that they're mirror images of each other, right? That's green closest, and then you got a series of yellows, a series of oranges, a series of reds, and you can actually see their individual lines. Everybody see individual lines here? Okay, so that's the key part here is individual lines. Okay, now that's what happens when you put neon in there. Okay, if I put a different gas. Okay, that's helium. That's what helium looks like. Okay, again, it's lines, right? There's fewer of them, okay? And the lines that you see are not at all like the lines for neon. But it's actually easier to see that this one's a mirror image of each other. Everybody see those? Okay. In your book, you talked about that Bohr could explain the colors that hydrogen gave off. These are the colors that hydrogen gives off. Okay? So it looks purple, right? Just look at it, it looks like a bluish purple, violet. But if you look at the lines, you see a nice dark blue line, a purple line, a red line. Everybody seen those lines? If you look real carefully, it actually does repeat. There's a purple and a red further out too. Look all the way over to a side. It does repeat. You only see the darker lines on the second one though. Okay, so that's purple. Okay. Is this the right one? No, that's not it. Okay. This one looks a lot like that, but it's not the same stuff. You should be able to tell. Can you tell if these two purple things are not the same thing? Right? A different series of lines off to the side, right? Okay. So what we've seen is different elements not just look different colors, that they're all, if you take those colors, they're always individual colors, right? They always come in those lines. That's what I need you to see. So now I'm going to hurt you. I'm sorry. How do you have those diffraction ratings passed back up for me, please?
I'm going to buy some of these.
Okay. I got them from Amazon. I think when I was buying them, when you buy them in groups of 40, you get them cheaper. Okay. Okay. All right. So. All right. So. Everybody saw lines, right? Everybody saw lines. Okay. Now, let's turn this off before I burn it out. Okay. So, by heating a gas, we saw that flames on Friday. Or with electricity. We saw that today. We can get it to do something different. How was what you saw in the individual gases different than what you saw when you looked at the white light? It was this, right? You didn't. There's a whole bunch of colors you didn't see. You just saw individual colors of light, right? That's what you're trying to describe in your notes is what you just saw. So it doesn't have to be my words. Okay. Now each element gives off its own characteristic colors. We saw that in the flames. Now here we saw a couple that look purple. but even though they both looked purple, they had completely different lines. We had two flames that looked red, but if I had taken those lights and looked at them through the diffraction grating, they would have had different lines too. It's unique. So they can be used to identify what kind of atoms there are. So if you look at the light they give off, everyone gives off its own special lines, like a barcode. Sometimes they refer to it as a fingerprint. Okay? So if you got a sample and you make it glow, you can tell what atoms are in there by which lines you see. And that's how we know what stars are made out of. If you want to figure out what's in the star, you can't just, go get a bucket of star and test it. There's a couple of problems with that. One, the stars are pretty far away. Two, they're toasty. Okay, but to show you the strength of this, in the 1900s, when they recognized this, they took sunlight and did this with it and saw what lines they got. And they found out a whole bunch of lines that matched up with hydrogen. But then there were some lines that didn't match up with any known element on Earth. Okay? No element on Earth did the lines match up with, so that told scientists there must be another element that we haven't found on Earth yet that's on the sun. And we will name that element after the sun. So since the Latin name for the sun is Helios, we'll call it helium. So helium was found on the sun before they ever found it on Earth. Okay? Because if you get helium to the surface of the Earth, it leaves. It's less dense than air, and it just keeps rising until it leaves the planet. So unless you dig a hole in the ground and separate the gases, because it gets the alpha particles get trapped in the same way natural gas gets trapped underneath an impermeable dome. So a lot of natural gas wells, or not a lot, a few natural gas wells have helium in them as well, and that's where we get our helium. Is from the radioactive decay inside the Earth being accidentally trapped. But they hadn't seen helium on Earth, but they knew there had to be a new element because they could see the lines in space. Okay? That's how far you can go to know what stars are made out of. You can predict that, hey, there's an element there. And actually, based on how bright they are compared to each other, you can tell how much of each one there is. So not just what's there, but how much of it, how bright it is. So hopefully, this is what you saw off to one side. Is that what everybody saw off to one side or the other? Okay, okay. Those are called line spectra. Spectra is the plural of spectrum. And these are what are unique to each element. Now, we were looking at the colors that they gave off. So these are also called emission spectrum. So when you wrote that that they couldn't predict the line emission spectrum of hydrogen, they couldn't explain the line emission spectrum of, they couldn't explain those lines you saw in hydrogen. Okay. Now, if you take those same gases and shine light through them and separate it with a diffraction grating, just like I did with the food coloring, if you do that with the individual elements, they're going to make an absorption spectrum. And the absorption spectrum is going to be the exact opposite of the emission spectrum. What do I mean by exact opposite? Everywhere it's black, you'll see the rainbow. And everywhere you see a color, there will be a black line where that color's not made, or that color's doesn't get through. So it turns out that the colors that an atom absorbs are the same as the color the atom emits. So there must be something in that atom that is that much energy apart, because it can absorb that color and it can emit that color. So the absorption spectrum looks like the whole rainbow with individual black lines. And that's how they know what the stuff in nebulas is. Nebulas is dust clouds in space. Well, those dust clouds are going to absorb the light as it comes through. And by how much gets absorbed, they can tell how much there is. So they can see what's in the nebula, even though the nebula is not glowing. You see what gets absorbed along the way. So, those are the colors. Those colors have to tell us about atoms. So, here's our explanation. How do we explain the colors we saw? How do we explain those lines? Okay. So when we say where does the color, where the electron starts, we're talking about where is it most of the time? Where is it the most stable? It's the most stable when it is as low as it can get in energy. And then in our ladder analogy, as low as you can get in energy is being on the ground. So that lowest energy they have is called the ground state. So electron starts off in the ground state, as low as it can be, its lowest energy. Okay. So now we're going to change that energy. And we're going to change it, and we're going to do the simplest model we can, the hydrogen atom. Okay. I know it's hydrogen because it only has one electron. It's got one electron, and I drew in 6 energy levels. I could have drawn in an infinite number, but 6 explains everything I need to explain. Okay. So the hydrogen atom. And we've seen that if I heat up or use electricity, or later on we'll see I can use light to move the electron up levels. The energy I put in takes that electron from its ground state up to a higher state. And it can jump to any one of the energy levels. And you can't pick ahead of time which one it's going to do. It's completely random. Everybody okay with that? So you put heat in, you don't know how far it's going to make it jump, but it's going to make it jump. Okay with that? It's not stable up there. It's going to fall back down. And when it falls back down, it gives off the energy as light. So as it's falling, it gives off light energy. So I put in heat, it jumps up, it falls back down, it gives it back as light. And it glows. And we see the colors. But we didn't see just one color. Well, that's because when it goes back, it doesn't have to go back all at once. It comes down in steps. It can come down in steps. It can fall from the 6th to the 5th, and then from the 5th to the 1st. Or it can go from the 6th to the 3rd, then the 3rd to the 2nd, then the 2nd to the 1st. Or it can go straight from the 6th to the 1st. And you can't control which one it's going to do. It's random. So, and each one of those steps it falls down is going to be a different energy. I didn't draw all the possible combinations, but you can see them all, right? They could fall any one of those, what, 5 factorial times, so 60? Oh, you're not supposed to talk about factorials and permutations. So this explains hydrogen. We saw individual lines. The fall from the second level to the first level was enough energy to draw an orange line. From this third level to the first level, that's more energy, right? So I'm going to get a more energetic, higher frequency. I'm going to get the green line instead of the orange line. From the sixth step, get the blue. Got the idea that why we get individual lines? Why am I never going to see this color? Because the electron can never be there. The electron has to be at this level or the other. It can never be here. And I know it's never there because if it was there, I would see that color. Does that make sense? So they know it's not there because they never see that color. Okay? Now, I've limited you to the visible spectrum. It happens through the whole spectrum. If you want X-rays, you pass electricity through tungsten. So when you hear that buzz, you hear that buzz when they give you an X-ray? You've ever heard that buzz? It's the same buzz as this makes. It's a transformer, taking the electricity, making high voltage. So just like the fluorescent lights make a buzz, for the same reason. It's just hitting it with really high energy electricity. So it gets really high energy waves. But those 3 lines are ultraviolet, visible, and infrared. Because the ones in the middle are the ones we can see. The ones that fall with less energy, we can't see. Because they're too low energy, that's infrared. The ones that fall further, we can see. We can't see because they're in the ultraviolet. So there's a whole bunch of lines we can't see. But they can detect. So, okay. And the further they fall, the more energy, higher frequency. Now, this is a simplified version, but it explains, it's a pretty good, clear explanation of where the light comes from. The light comes as it falls down. Okay. Now, simplified in that we only talked about hydrogen. And when they said that, we read that Bohr could calculate the pieces for the Lyman series, okay? He could calculate if the electron is moving at this speed around the nucleus, when it falls back down to another place, it's got to give up this energy. And that much energy, based on the electron moving around in circles, that much energy came out exactly to the colors of lights he should see. So he could do the math for an electron going around hydrogen. But as soon as you go to helium, you run into a problem. Because then you have an extra component. With hydrogen, you only have the attraction between the proton and the electron. With helium, now you got the positive nucleus, and you got an electron, but you got another electron that is not only attracted to the nucleus, it's also repelled by the first electron. The 2 electrons repel each other. And if you ever talk to anybody in physics, as soon as there's 3 things moving, you don't want to do the math. Because it's impossible to solve. Okay? So the scientists never solve 3-body problems where 3 things are pulling on each other. They always try to simplify it so just 2 things are interacting. Couldn't solve the math for the extra particles. Because every time it went around, over here it wouldn't repel as much as it would over here. And you have to take that into account. And it gets really messy really fast. Okay? So it didn't work. But What is light? Because I've contradicted myself. And if you're confused by my contradiction, you're exactly where you're supposed to be. You're supposed to be confused. Because you should stay confused the whole time. Because light is a particle. It comes in little chunks. We saw that yesterday. We saw that with the photoelectric effect. That light coming in chunks is the only thing that explains the photoelectric effect. Because you have to have a chunk big enough to knock the electron off, otherwise nothing happens. And it doesn't matter how many small ones you send. If one can't knock off an electron, it's not going to happen. You can't team up. Yeah. Light's a wave. The fact that you see rainbows, the fact that you saw the rainbows on the projector today, was proof that light is a wave. So yesterday, we went through the whole thing to talk about the photoelectric effect so I could prove to you that light's a particle. Now I've said that the fact that you see rainbows is proof that it's a wave. I want to show you how it's proof. Okay? So a piece of plastic you were looking for were called diffraction gratings. Gratings just means that they've got like a grate, like you put stuff on the grill, that they've got lines scratched into it. It just works out to about 12,000 lines per centimeter. Okay, so when light passes through or reflects off a series of thinly spaced lines, it creates that rainbow effect. And that rainbow effect is proof that it's a wave because you can only get that rainbow effect if waves are interfering with each other. Now, when we think of the word interfere, we think of getting in the way. But for a scientist, interfere means that waves, when they encounter each other, they interact. So if I have a 2-foot wave running into a 2-foot wave, the 2-foot wave, one 2-foot wave will go on top of the other 2-foot wave, and I will get a 4-foot wave. But if I have a 2-foot wave run into a 2-foot trough, they will cancel each other out, and I won't have a wave at all. So those two are called constructive interference, or destructive interference, makes it smaller. Okay. So let's look and see why waves interfere. Okay. And the easiest example to give is a pretty simple example. I'm showing you the top of a wave, and then there's a barrier it's moving towards. So as it goes towards that slit, what's it going to be like coming out the other side? You're going to get a curve, right? See that curve? Okay. Uninteresting. Put 2 holes in. It gets a little bit more interesting. Because with 2 holes, I'll make 2 curves. And 2 curves will eventually run into each other. And right there, that's a crest on top of a crest. So right at that spot, it would be twice as tall. And right here, just in front of that there'd be a trough on the other wave. So the trough would hit that crest and cancel it out. Make sense? So they're going to add up here twice as high, and right behind it, they'll cancel each other out. So the crests add up. The lines interfere with each other. Okay? Now, if I make several waves, I'll get several curves, right? And when those curves run into each other, they make up a pattern. There's a pattern. And if you drew a wall across here, you would find that the double high waves would work right down the middle, but then slightly behind them, they would all be canceled out. So that's interference. Now we see it with waves. So if I turn on the drippers, okay, making two waves. And what you're seeing is the blue is the top of the wave, the black is the bottom. And you'll see that I make a wave top, and then right behind it there's a bottom. And you'll notice that the blue stays added up all the way right down the middle. And then right behind it and off the side is where the crest of one runs into the trough of the other, and you get a null zone where there's no wave. So if you walk down this beach, there'd be waves here, no wave here, waves here, highest right there, and then no wave there. You would not want to build your house right here. Does that make sense? Okay. So with slits, you get the same thing. And notice there's a dead pattern, that there's an angle by which they do it. And turn the frequency up a little bit. Move my slits a little closer together. Oops. Okay, so see those dead zones? So it goes wave, no wave, wave, no wave. And as I change the frequency, it changes where they add up. That now my null zone is closer together. If I make the wave longer, still adds up down the middle, but the null zone's way over here. It's wider. So, the strange thing here is they're just going to make it a circular diffraction pattern. So if I turn on the light, you'll see that you get alternating dark, light, dark, light, dark, light. That's an interference pattern. That's because waves interfere with each other. Okay? And if I change the color, change the wavelength of the light, as I make it red, it adds up further out. And if I make it blue, it adds up closer together until I get to purple. So that when you were looking at the rainbow, you could still see the white light right in the middle, right? But then off to the side, the purple would add up closest together. So you'd see purple right next to the light. The red would add up furthest apart. So you see red on the far side. So the fact that when you projected through that diffraction grating and you saw a rainbow, that is proof that light is a wave. Because only waves can make those interference patterns. Okay. Because, well, that's what a person looks like, huh? So, if you have the whole rainbow, they're going to add up in different places. So, light shows interference pattern. Light is a wave. Oh, here's a better simulation of it. I know I had one. Okay. So here I've got the same type of thing. They're showing them as waves. And if I change the wavelength, okay, so you see red, so the color always adds up down the middle no matter what color it is. But red adds up further away, blue adds up close together, and purple right up against it. So as you went out from your light and you saw the rainbow, first you saw purple, then blue, then yellow, then red. And it worked in both directions. Purple, then blue, then yellow, then green, then yellow, then red. Right? So that's what you're seeing when you see a rainbow. So a rainbow is always proof that waves are interfering with each other. Now, how the rainbow you usually see works, it works because the sunlight comes into a raindrop, so the sun is always behind you when you see a rainbow. Okay? When the light comes in, it hits here, and every time it gets to an interface between water and air, it bends. Hits the back of the drop and bounces off, hits here and then bends again, comes back to your eye. So light comes in, bends a little, bounces, comes out, bends again, and you notice both those bends are in the same direction. And that's important because red bends more than purple. Okay? So that if the red bends more than purple, it'll make it so the red goes in a little bit, and when it bounces off here, and then it's going to bend a little bit more, and it means that the red's on the outside, and the purple would be on the inside. Because all the other colors are going to interfere. It's about the fact that they bend different amounts. So the two ways you can make a rainbow is to bend it with an interface, or force it through between slits. So anytime you see an interference pattern, you know it's a wave. Okay. Now, where's that? Show it to me. So, a guy named de Broglie, I'm never going to ask you to do this, but I'm going to show you. Just use some basic pieces and did substitution. And with substitution, you can get to here. Lambda equals h over mv. That's not a nu. That's a v. Okay. So that says the wavelength equals Planck's constant divided by mass and velocity. And that means anything that has a mass and has a velocity has a wavelength. You have a mass. You're sitting on the surface of the earth and it's spinning around, so you have a velocity. You have a wavelength. Oh, you have a wavelength. Matter is a wave? I just spent a whole chapter talking to you about matter being a particle. Matter's a wave? Guess that's got to be tomorrow. Matter's a wave? Do the wave. I am the wave. I asked for it. I know my job to say something, right?